Okay, welcome to the next class on multiple view reconstruction. Last time we talked about finding correspondences in images. So the question is that we want to do the reconstruction assuming that we have corresponding points. So we will tackle the reconstruction problem by saying, let's say we have two images from different viewpoints and we know which points are in correspondence, and then we can try to figure out what was the camera motion and what's the 3D location of these points. This is the classical approach to do image-based reconstruction, but of course the key prerequisite is that you find correspondences. So you are given, say, two consecutive images, maybe from a video camera or just two photographs taken from two viewpoints, and you want to find how did points move from one image to the next. And I already talked about the differences between, on one hand, the small deformation case where we assume that we have small motion, and then the wide baseline or large deformation case. These are two distinct cases, and these are two extremes of the problem, and depending on what scenario you have, you will select different algorithms and different methods. Today, I will start with a small baseline or small displacement case, and then mention a little bit about the wide baseline case. The small baseline tracking case is actually the scenario that is often referred to as optical flow. So you're given a set of images and you see from one image to the next there's a little displacement. It's not very much. In more challenging scenarios, the displacement may be larger, but then methods will still tend to work. And what you see here is results of a tracking algorithm where you track a selected set of feature points. So only these red points are superimposed on the image and they're tracked from one frame to the next. An alternative is the wide baseline case and the non-rigid deformation case. And here, the dense tracking, this is what I showed you here, is deformations that actually, where you have a substantial displacement from one frame to the other. So there's actually a lot of changes, say from this frame to that frame, a lot of changes in coloring, in partial occlusions of structures, and still you can, as you can see, you can actually track points even with larger displacements. This is the distinction between small baseline and large baseline. Today I wanted to focus on algorithms that are designed for the small baseline case. To what extent they still work for larger baselines? Of course, you can imagine there's a continuous transition between small displacements and large displacements, and how much these methods still work in the large baseline case really depends on how you implement them. And so often it is hard to judge, is the method of Lucas-Kanade, of Horn and Schank, is it a good algorithm or not? And if you look into the literature, into the community, you'll find very diverging opinions as to whether these methods actually work well. The reason is that whether they work well or not depends on who implemented them and how they implemented them. And this is something that we often find in research, that the devil is in the detail. And that I can take a method that was published and I give it to two different students. Student A implements it and it appears the method doesn't work at all. Student B implements it and it works like a charm. So unfortunately, it really depends on how you implement things. So today I wanted to talk about one of these two seminal methods that really pioneered the field of flow estimation, the Lucas-Kanade method and the Horn and Schank method, published both in the same year in 1981. And today I'm going to talk, as I said, about the Lucas-Kanade method. Here's the key assumption, and in fact these two methods of Lucas-Kanade and Horn and Schank are not so different in the end. They have the same kinds of assumptions more or less. And clearly you have to make assumptions. I mentioned that last time. If you don't make any assumptions from one image to the next, let's say you allow objects to change their color at any given moment, then you will never find correspondence, right? If you have chameleon-like objects that arbitrarily change color, then in one image they may look very different from the other image. So we got to make some assumptions to find correspondence. And the simplest and most basic assumption is that so-called brightness constancy assumption, or brightness constancy constraint. And the assumption here is that the brightness of a moving point is preserved. So I'm saying moving point, but in what follows we'll actually assume that the camera is moving. And so objects point, at least on the camera, on the image plane, will move. Because the camera is moving. I mean, this is interchangeable. When you do correspondence estimation, it doesn't matter where the displacement comes from, whether it's from the camera motion or from the object motion, is in some sense exchangeable. And so we assume a point is moving. X of t is the coordinate of that point at time t. So that is a point corresponding to some structure, some in the image. And then we assume, in addition, that this brightness is constant of that point. That is a fairly strong assumption, and in reality it is almost never fulfilled. Right? If I take real-world images and then the illumination changes a little, the sun comes out, the sun disappears behind the cloud, brightnesses are going to change. The hope is that they will not change substantially. The hope is that they will change, but maybe only very little. Or that the brightness changes are gradual. For example, if you have a fast camera and then the lighting changes because the sun comes out, that's a fairly gradual effect typically. Not so if someone enters the room and switches on a light. And also not so if you have neon lights or other types of lights that actually oscillate. And if you ever have the chance, you should try that. Just film a static scene with a camera and then compare the images. And surprisingly, I was amazed when I first did that, the brightnesses changed substantially. For example, if you go back to this example here, the brightness here and here are not actually the same. So if you take the brightness of any point in the background, they have different intensity. Because somehow, due to artificial lighting oscillations with a specific frequency, they change. And so these are some of the problems we face when making brightness constancy assumptions. But the issue is, and this is often a case in any field of research, you have to make some assumptions to get anywhere, to estimate data, to estimate model parameters here, motion, you have to make some assumptions. And even if you know the assumption is not fulfilled, as long as you don't have a better assumption, you stick with it. And maybe you start thinking, is there maybe a better assumption that is some property that is constant, that is preserved over time, and we'll see later on that one can do a little better. So we assume that this quantity is zero. Note that there is a twofold dependency on time. The first dependency is that I evaluate the brightness at a different pixel at any given moment, at the pixel where the object is at that moment. And I evaluate the brightness at later time, so that is the second component time. So I take the first image, let's say, and then the second image. So this quantity is constant for all times, and as you may recall from analysis, if a property is constant with respect to time, you can also say that the derivative with respect to time must be zero, must vanish. Any quantity that is constant has zero derivative, meaning if I take the derivative of this expression with respect to time, it must be zero. Interestingly, there is this twofold dependency on time. So if I take the time derivative, I have this to take into account. Firstly, that I take images at later times, and secondly, that I evaluate at locations that change with time. And the way I do this is basically applying standard chain rules of differentiation. For the first component, I have the derivative with respect to the first component, x, that is nothing but the gradient. So for those who don't remember, the gradient nabla I is nothing but, in a two-dimensional image, the derivative of I with respect to x and the derivative of I with respect to y. So it's a two-dimensional vector containing the two spatial derivatives. Here, when I write x, it actually has two components. It's a 2D point. So this is a 2D vector, the spatial gradient transpose times, and then the inner derivative, that is dx by dt. How does x change with t? And this is an important quantity. That is the velocity that we're interested in. It is the quantity that tells us how does x move in time. And this is what we want to find out. So the goal is, from the brightnesses, to figure out what is the velocity. How do points move on the image plane? And so that is exactly the vector we are interested in. We'll call it v later on. So this is our velocity vector v. But then we have the second dependency on time, that is just the partial derivative of I with respect to time. So here you may have encountered that in analysis, and you may not have fully captured that at the time, the difference between the straight d and this curvy d, or del it's sometimes called. The straight d is the total time derivative. It means it takes into account any time dependency of this expression, either in the first or in the second component. And this here means just the derivative of the brightness function with respect to the second component. So these are two distinct issues. Please keep that in mind. It's not random that I put the curve d here. There is a reason for it. And so this whole expression, that is the total time derivative, must vanish. And this constraint, this equation here, it is an equation that couples, as you can see, the spatial brightness derivatives and the temporal brightness derivative with the velocity vector that I'm interested in. The question is, can we solve this for the velocity vector? This equation is a very important equation in the computer vision field. It's called the optical flow constraint. Sometimes specifically the differential optical flow constraint, because we got it from this brightness constancy assumption by differentiation. But if you go in the literature, you'll find a lot of different terminology used exchangeably. Sometimes this is called the optic flow constraint. Sometimes this is called the optic flow constraint. If you want to differentiate, it's you can say this is the differential optical flow constraint. So it is the brightness constancy assumption, but on an infinitesimal formulation. Unfortunately, and we will see this is the big problem for optical flow estimation, we cannot solve this equation directly for the velocity vector. Because it's written here, but you cannot invert this. This is a scalar product of two vectors. So the only thing that enters the equation here is the projection of the velocity onto the image gradient. And so, in other words, what we have here is essentially the component of the velocity vector in direction of the gradient. The component of the velocity orthogonal to the gradient, we don't have. We don't see it. It vanishes. So any flow component that is orthogonal to nabla I is going to be 0 here anyway. Maybe to give you an intuition what that means practically speaking, and this is a common problem. Let's say you have a black object on white ground. Fortunately for us, the world is not made of black objects on white ground. But in the 80s it was, at least in the computer vision community. People were looking at scenarios, kind of artificial, idealized scenarios, and they said, I assume I have a black square moving on a white ground, and now I want to estimate motion. And then people stumbled and realized they can't do it. And the solution is, there are no black squares on white ground, at least not in the world I live in, fortunately. So typically we have enough texture, and so even my shirt that is black, if you go close up, you'll see slight brightness variations, and these are very important. Why is that? Let's assume that you see a black object on white ground, and you want to estimate the motion for that structure. There's multiple problems. If you want to estimate motion for the interior of the black region, so you zoom in, you take a close-up of this black region, no matter how the object moves, you're not going to see anything. It's just black, right? So there is no way you can estimate motion by just looking at this patch and saying, how does it move? There is no brightness changes. There is no way to estimate motion. Now let's assume we look at the edge and say, can we estimate motion here? If the object moves in this direction, you're not going to see anything, right? It just moves like that. So the observed structure in your little window of estimation doesn't change. Whereas if the object moves in this direction, and that is the direction of the gradient, the image gradient is basically pointing in this direction, that motion I can see, because in 1 second later the observed structures look different. I have more black here and less white. So I can see motion in this direction for an edge like that, but I cannot see motion in that direction. And that means in general, if I have a velocity, say this point is moving in this direction, all I will be able to see of this velocity is the component of that velocity in direction of the gradient. And the component of this velocity vector that goes along the edge, I don't see. And this problem, we'll get to it a little later, is called the Aperture Problem. It's a very important problem because it tells us by looking up close up how much can we actually estimate. And it tells us that if we have a gradient only in one direction, then we will only be able to see motion in that direction. And so this is kind of the more physical meaning of the fact that you cannot solve this for V. You cannot extract V from the scalar product. But we will see with a few additional assumptions you can get around this issue. And the additional assumption that we make in order to find a meaningful velocity vector is that we will assume that not just at that location we have the constraint, but we have the same constraint with the same velocity vector in a certain neighborhood around that point. And so the idea is that we have a neighborhood, and furthermore the idea is that in the neighborhood we look at, we have structures in different direction. So if you look into this whole neighborhood and say, I want one velocity vector that is consistent with this optical flow constraint, then you will be able to estimate the full motion. Because you will see in this area the component of the flow in that direction, and in this area you will see the component of the flow in the other direction. And so if you search for one flow vector that fulfills this constraint for all points, then there is a unique solution. In this scenario, if your window happens to be on an edge, or even worse, in a constant brightness area, then you're screwed. Then there is no motion that you can estimate. And so the assumption that we will make, in addition to the brightness constancy, is the assumption that the motion is actually constant in a certain vicinity. And this is the assumption that was made by Lucas and Kanade. So the assumption is that we have exactly this optical flow constraint. Here I wrote it again. For all points, let's call them x prime, in some window around x. Ideally, as I drew here, the window would be a circle because you don't want any directional dependency. In practice, of course, you take a square because it's simpler to implement, because you want to sum over all points in that window later on, and then if you have a square, you have 2 for loops. So in the drawings I do circles, but in the implementations you typically take a square, not to complicate things too much. And so we assume that this constraint with the same velocity vector v holds for all points in that window. So we have a point x, let's say this point x here, and this here is the window w of x around that point. And there you see already there's an implementational aspect. How large do I choose the window? Do I take a large window? Do I take a small window? There is no unique answer to that. It really depends on the application. For example, if you have a lot of structure in a local area, you don't need a large window. You have enough information there. But if you're really looking at the black square on white ground, your window should be large enough to encompass some corner of the object. In applications, you can typically check if your window is large enough. We'll see in a second where that emerges. You will figure out if your window has a purely constant area or not. And then you may need to increase the window size. But typically there's a trade-off. I don't want to take too large windows because then I lose the localization. In practice, motion will not be constant over the whole window, right? If I have a complicated motion, then, points here don't move exactly the same way as points there. There's a rotation there. So, in the vicinity, they tend to move more or less in the same way. But if I take a larger vicinity, that is no longer true. So the assumption that V is constant in that window becomes less and less true the larger I choose the window. And this is where you have a trade-off, and then it depends. And this is why I'm saying, whether these methods work depends on who implements them and how you implement them. So we have this optical flow constraint in the whole window. The problem is, of course, in practice, this flow constraint doesn't hold. First of all, the intensity is never perfectly constant, because of lighting changes, because of specularities, all sorts of nasty effects, because of noise. Just you take a camera, the sensors have a certain noise level, and so even if they see the exact same point, even if the brightness is perfectly constant in the world, the camera adds noise, and then you measure slight variations of that brightness. And so these constraints are not exactly fulfilled, and the velocity is typically not exactly constant in that window either, meaning this constraint will never be perfectly fulfilled. But what you can do, and this was done by Lucas and Kanade, and to some extent in a similar fashion by Horn and Chunk in '81, is to say, well, it's not exactly zero, but we assume it's close to zero. And what we do is we try to find a velocity vector such that the constraint is as best fulfilled as possible. Now, what that means as best as possible is again a matter of technicalities, and there's different choices to do that. What Lucas and Kanade did is they minimized the least square sum. See, what we have here is nabla I transpose velocity plus the time derivative, and that is supposed to be zero according to the flow constraint. And what we do now is we take this expression, we take the norm squared and say that should be small. Ideally it should be zero. In reality it will not be zero, but we'll assume it's small. It's very much like if you do equation solving, you want to find a solution to an equation, but if it doesn't have any, you want to find some x that is as close as possible to making the equation true. And this is in some sense what you do here, and this is called in this setting a least squares error. One should say nowadays in accurate optical flow estimation algorithms, one does no longer do this today. There are improved methods. For example, one small detail is the square here. In practice nowadays you would not put the square. You would just take the norm but without the square, and you tend to get better estimates. So whether ideally the constraint should be zero, the question is how do we penalize deviations from that zero? Do we penalize them quadratically? Do we penalize them linearly, etc.? So there's many choices here. Lucas and Kanade started with quadratic, and this is typical in science. When you start to solve a problem, you make some assumptions and you implement it in some fashion, and typically even the authors who did it, Lucas and Kanade for example, most likely knew that this choice is somewhat arbitrary. But the issue is, in practice, you want to get some solution first. And so you start with, in some sense, the simplest, and then you move on later on. Once you see it works, then you say, how can we improve it? How can we get a better cost function? This is called a cost function or an energy, and this is why it's often referred to as E. Large E stands for energy. Why these terms are called energy is a bit of a long story, but a lot of these optimization techniques are inspired from physics, and in physics these expressions are called energies. And so this is why sometimes I'll refer to this as an energy, sometimes as a cost function. What we have here, and this is important, is it's a mapping that assigns to any velocity vector some cost, some quality. And the idea is that if the velocity vector is a good one, then this expression should be small. And if the velocity vector is a bad one, then this expression is going to be large. And what's also typical for energies in computer vision is that they're always positive or non-negative. So the best you can do ever with any velocity vector is to get this to 0. If this is 0, it basically means the full flow constraint is perfectly fulfilled. It's exactly 0. In practice, it's not going to be 0, it's going to be larger than 0. And so what I want to do is, once I set up, and this is what Lucas and Kanade proposed, is they set up this cost function and said, find the vector v that minimizes this expression, that fulfills, or as best as possible in this quadratic sense, fulfills the flow constraint for all points x prime in the window around x. This also, I again should not confuse you that there is an integral here. If you go to the Lucas-Kanade paper, the 81 paper, there are no integrals there. There are sums. But you know from analysis that an integral is essentially a sum. It's the same thing. So you could just as well sum over all x prime. The reason why I prefer integral notations is that I prefer working in a continuous space. Summing basically means you have a specific grid that you sum over. You have points on a grid. Once we write integrals, we have a notation that is independent of a specific grid. But of course, when you really implement it in the computer, you have a finite set of pixels and you have a sum. So there's slightly different communities. Sometimes people write sums, sometimes integrals. It's to some extent exchangeable. One reason why least squares are extremely popular. Who has heard of least squares estimation before? Yeah, a lot of people. Obviously, this is a common approach in science, and here it is the least squares approach to estimating flow fields, where you say the optic flow constraint should be fulfilled in a least squares sense. One reason why least squares are popular is there's a number of reasons, but one is they have a quadratic cost function. See this expression? We want to see it. Often when you look at energies, and this is a fairly simple energy, in computer vision they can become longer and more complicated. And then it's helpful to have some strategy of looking at equations. This is typically important when you see math and equations at a first glance. They can be a bit overwhelming, not maybe this one, but other ones that are longer and bigger. What's important is to see the structure in these equations. And here, we want to optimize whatever this is as a function of v. So we have to check where is the v in this expression. It's right here. And this expression is linear in v. So this is a function that is linear in v. And then I square it. So what I get is something that is quadratic in v. And how do you do minimization? You remember from analysis, the energy at the minimum, the derivative must be 0. So E is minimal if dE by dV is 0. And now this is why least squares are popular, because they lead to a quadratic cost function. And then taking the derivative leads to a linear equation, a simple linear equation. And there's standard solvers in MATLAB. Here's what it looks like. So this is 2 2 times mv plus 2q equals 0. M and q are these things here. And it's not difficult to get to this, maybe to show you a little bit. So what we have here is nabla I transpose v plus it squared. And if we square that, we get v transpose nabla I transpose v plus 2 times the mixed term, time derivative, nabla I transpose times v, plus some terms that don't actually depend on v, some constants. And so here you see this term is quadratic in v, v transpose some matrix times v, and this term is linear in v. So we have one quadratic term, one linear term, and if we rearrange these terms, we can write v. This we call in addition we have the integral over x prime, but the velocity is the same for all x prime, so we can pull the integral inside here. So we have v transpose the integral over this times v, and similarly we can pull the integral in here. 2 times that expression times v. And then if you solve this, if you take the derivative with respect to v, you get exactly this equation. 2 times that matrix here, we call it m times v, and plus 2q, and q is this expression here. So we have that linear equation when we take the derivative and set it to 0. Linear equation, and plus it's an extremely simple linear equation. It's a vector that only has 2 components. So it's a linear equation system consisting of 2 equations, which you can write in matrix form, and m is nothing. This is a 2 by 2 matrix, right? Nabla I is the gradient that I wrote here, so it has 2 components, times the transposed is then a 2 by 2 matrix. So this is not the scalar product of the vectors, but the so-called outer product. A vector times its transpose. So this is a 2 by 2 matrix. This is a 2D vector, because this is 2D. This is the time derivative is a scalar. And as you recall from analysis, if the matrix M that we have here is invertible, and how can you check it's invertible? You can check if the determinant is non-zero. If it's non-zero, I can invert the matrix, and then I can solve this for V. And I just pull this on the other side, and I get V is minus m to the minus 1 times q. So I have a solution to the optical flow problem, which I got by assuming that the optical flow was as small as possible. This flow constraint was as small as possible for all points in the window. And you see, we need the points in the window to construct this matrix and to have an invertible matrix. If you don't have the integration over the window, but just stick with that one point you're looking at, then you don't have the integral here. You just have nabla I transpose, and that is not an invertible matrix. Whether M is invertible is a good question. We can see already cases where M is not invertible. If the gradient is 0 for the entire window, and that is the case if we have a window on a completely black area or on a completely white area, then the gradient is going to be 0 for all points in that window. And then also the whole matrix M is going to be 0. So that's really the worst case you can have. Then the matrix M is 0, and that means for this equation, V can be whatever you want it to be. The equation is going to be, it doesn't affect the equation. Actually, it's going to be fulfilled, right? Because this, if nabla I is 0, then Q is 0, M is 0, everything is 0, no matter what velocity you take. And so this is not surprising. This is the mathematical, basically the mathematical view of the fact that if you look at a constant brightness area, you will not estimate velocity. But as I said, in the real world, things are textured typically. We don't live in this black and white world, we have a world where things are textured, and even homogeneous colored structures will have varying appearance once you take images. And so typically when you take a window in a real world scenario, the determinant will be non-zero. And then you can invert the matrix and you can estimate a flow vector. I should say there is one additional case, and that is if the gradient is constant in the image, in the window. Constant, or at least constant up to a scale. Let's say we have this aspect of looking at an edge in the image, so a black and white edge, and the window is somewhere over the edge, then all gradients, no matter where you estimate them, will be pointing in that direction. And then you have a somewhat degenerate case. You will have a matrix M that is not zero, but it only has one eigenvalue. So there is one direction, and that is that is the direction along the edge that's going to be mapped to zero by this matrix. Right, because if you apply this matrix to a vector that is orthogonal to that gradient vector, and the vector points in the same direction for all points in this window here, then any vector pointing in that direction will be mapped to zero by M. And so it will not affect the equation here because it will be mapped to zero, meaning velocity components in that direction can be anything. We don't see them. We cannot estimate them. And so you see all of these three cases, the case that I'm looking at the constant brightness area, the case that I'm looking at an edge, and the case that I'm looking at the corner, they are all captured in the structure of that matrix M. In the question, is M exactly zero, as here? In M having just one eigenvector, one eigenvalue, and the other direction being mapped to zero, or two eigenvalues, and then I can really estimate motion. Only in that third case will the determinant be non-zero. And only then can I estimate a full velocity vector by matrix inversion. So basically the way this was proposed, I think in the Lucas-Kanade paper they focused on translational motion. So let's call this translational vector B. I called it V earlier. So B is a vector that is constant for the window. So we have just translation. And then as I showed you, we can set the derivative with respect to B to zero, and we solve for B by doing matrix inversion, assuming that M is invertible, that matrix. As I said, you can also use the exact same approach or the similar approach to estimate more sophisticated motion fields. For example, I can assume, if I'm not happy with the constant motion assumption, I can assume that the velocity in my window, let's say this window, is rotational. For example, rotating like this, or more generally, some kind of affine motion. And as I showed you earlier, we can model the motion at any pixel x prime as some parameterized motion model with a matrix S that depends on x prime and some parameter vector P. Let's go back to where I introduced the affine motion last time. Here it is. This is S times P. S is such a matrix, and P is this vector with 6 components. And these 6 components model, among other things, rotational motion or divergent motion, skew motion. There's different kinds of motions that can be represented by 6 parameters. So instead of having 2 parameters for my window representing translational flow, I can have 6 parameters that model a more rich flow field that actually changes. So the flow at this point, and at this point of the window are not the same. They're different, but what is the same for the whole window are the 6 parameters here. And if I use that, the flow being S times P in here, then I just insert that in the exact same energy. And why is it, why did I say this is essentially the same approach? Because what I'm now interested in is what are the 6 parameters for the flow in that whole window. And this is the vector P, a 6-parameter vector that I want to estimate. And it's the same approach, mathematically speaking, because this is linear in P here. And once I square it, it becomes quadratic in P. So I can use the exact same strategy. I can, multiply out this expression. I've done it for the linear, for the constant motion case here. You can do the same for the parametric motion case. And then, since this is all linear in P, squaring it makes it quadratic in P. So I have an equation that is quadratic in P. If I set the derivative to 0, this equation, the minimality principle, is a linear equation in P. And I can again solve it by matrix inversion. The difference is, here, the matrix I had to invert was a 2 by 2 matrix, the matrix that you have here, M, that I have to invert. In the parametric motion case, it's a 6D vector, and it's going to be a 6 by 6 matrix. But with modern computers, that really doesn't make a big difference whether the machine has to invert a 2 by 2 matrix or a 6 by 6 matrix. That's cheap to do, it's fast. So you can do that also in real time. And this is one of the reasons why Lucas-Kanade was popular, in particular this translational model, is because it's simple and it's fast. Least squares is something that every engineer understands and can implement. And here, even once I add a parameterization, so I'm allowing a non-constant flow field, but a flow field that is parameterized by 6 parameters, that includes rotational motion, divergent motions, etc., I can still apply the same technique, the same algorithm. I said it's simple to implement. That is actually not exactly true. First of all, the matrix is not always invertible, and the question is, how can we figure out if it's invertible and when is it invertible, etc. This you have to test. And in addition, typically the way you solve this is you find a vector B, but this is always using the small motion assumption. In real-world scenarios, the motion may not be that small. Small here really means it should be about 1 pixel and not really more. And especially with high-resolution cameras, motion is typically much more than 1 pixel. It's not going to be 1 pixel. But what you can do is you can do a coarse-to-fine implementation. You start on a coarse scale, and on a coarse scale, so on a coarse resolution, you coarsen both of the input images where you want to estimate the flow. And if you have fewer pixels, larger pixels, then motion, even larger motion, on a very coarse scale may still be 1 pixel, 1 big pixel, if you will. And then you estimate the motion on that coarse scale, and then you warp the images based on that coarse motion and continue on the finer scale. So you basically iteratively remove the large components of the displacement, and on a finer scale you only have smaller displacements. But you can imagine whether that technique works depends on how large the flows are. It depends on the image structure, and it really depends on how you implement this coarse-to-fine strategy. And this is actually, for many years in the 90s and 2000s, people were arguing that Lucas-Kanade and Horn and Schunk were not very good flow estimation techniques. But then later people, improved the coarse-to-fine strategies to solve them, and it turned out with a better coarse-to-fine approach, you can actually estimate much more accurate flow fields. But so that's where the devil is really in the detail. Now let's look at the question, is the matrix M invertible? This matrix M is typically called the structure tensor. I think it has multiple names. Sometimes it's called structure matrix because people say, well, tensor sounds a bit sophisticated. Tensor is kind of the generalization of matrix, but here it's a 2 by 2 matrix, so it's just a matrix. Sometimes it's called structure matrix, often structure tensor. I'm not sure why people selected the term tensor here. Maybe they wanted to make it look more sophisticated. I mentioned the aperture problem, the problem that you cannot always estimate motion by looking at a small window. The gradient may be 0, or it may be constant, or at least constant up to scale in the whole window. We saw that this structure tensor, this matrix, for having a unique solution to this equation, it has to be invertible, and that means the determinant must be non-zero. Interestingly, once you implement this with real-world data, you'll find the determinant is always non-zero. If ever you see this, these kind of conditions in papers, you got to be careful. You know, when is a digital number ever exactly 0? Let's face it. You know, you have machine precision, you have a little bit of noise, and immediately, you know, you give me any matrix estimated from real data, it's going to be non-zero determinant. So in practice, of course, you don't want non-zero, you want something that gives you a reliable inversion. If I have a matrix that has 2 non-zero eigenvalues, but the second one is tiny, very tiny, then the inversion is what's called ill-conditioned. That means the solution of the inversion is strongly dependent on noise, because the size of the small eigenvalue will be strongly affected by even tiny noise fluctuations. And so you want to make sure it really is sufficiently non-zero in some sense. I mentioned if the determinant is 0, if we have the, say, in artificial image data, that can happen, not so much in real data, but if you take artificial data of that black square on white ground, then you will find that it can be 0. Then the determinant can be 0. For this case, for example, of the edge, that will happen, but then we can typically still estimate what's called the normal motion. That is the component of the flow in the normal direction. But if the determinant is non-zero, we can compute the flow vector, and so this is what's typically done in practice, and this leads to the feature tracking, for example, that I showed you in the beginning of this teapot scene where we track the points. This is essentially what's done there. You compute the structure tensor for each point in the image plane. That is not so demanding. This is always important when you want to do something fast. It helps to look at how many computations do I have to do. Here I have, for each point pixel in the image, I have to do a computation. That is a bit demanding because there may be lots of pixels. But what do I do? Just the spatial derivative in x and y direction. And then I do this 2x2 matrix. That's not too bad. Typically derivatives in practice, I'm not going to go too much into detail. If you take classes on image analysis, you will learn more about that. But the way you implement the x derivative, so Ix is the spatial derivative with respect to x. In practice, you say you take a pixel ij and you subtract I of I minus 1j, so that difference to the neighbor. There's many ways to do that, but the spatial derivative, how does the intensity change from one pixel with coordinates ij to the next I minus 1j is just the difference. There are many ways to do derivatives. This is the simplest one, but you can also, you know, if you have the pixels here in your discrete image, and this is pixel ij, here's I plus 1j, depending on how you want to, and here's I minus 1, or typically I plus 1, I minus 1 here. You can also do symmetric differences if you want. You can also say I plus 1j minus I minus 1j, and then over 2 because the distance is 2. So there are many ways to discretize, but this is essentially very simple to implement. That's important. It's just differences and products, so it's very fast, very simple. And then what you do is you compute the determinant, and you check, is the determinant sufficiently large? So not, is it non-zero, of course, but is it larger than some threshold theta? And again, we have a parameter here, a threshold, and you can imagine how many points are considered. It depends on how you set the threshold. And the question of what is the right threshold will depend on your images, right? If I scale all images by a factor of 2 because I have a stronger contrast in my images, then you can clearly see all these expressions will increase correspondingly. They will actually grow, as you can see here, quadratically. And then, of course, I have to adapt the threshold. And so this is quite common with such approaches. It's not always trivial to find parameters that work in a random scenario. You'll have to adapt the parameters of your algorithm to whatever scenes you typically work in. And then you hope that with the same parameter value, it works on a sufficiently large spectrum of images. So we have that parameter, but then we mark all points where the determinant is invertible in the sense that where the matrix is invertible in the sense that the determinant is sufficiently large. And then you can assign to that pixel at that time a flow vector that is given by the inverse of that 2 by 2 matrix times this vector that we called Q on the previous slide. Now what you can do in a tracking scenario is, if you identified points in the first frame and estimated their motion in this manner, then in the second frame at time t+1, you can just repeat that for the points x plus b. So you take the same subset of points that you estimated the motion for at time t, and where should they be at time t+1? They should be at the location x plus b, and so you repeat the whole process there. And that will accelerate things because you, starting from time t+1, you're not going to have to look at all pixels anymore. You just look at those where you're tracking. And that drastically accelerates because now the speed is linear, not in the number of pixels of the image, but in the number of tracked points. And typically you're going to track, say, a few hundred points instead of megapixels, right? So this will make things very fast. The problem is, if you do that, of course there's a lot of technicalities you can imagine. If you do this tracking, sometimes the structure, the matrix, will not be invertible any longer because maybe that point got into an area where the contrast in the image got so low that the gradients were so small that all of a sudden the determinant was below the threshold. You lose that point. And so if you just track the points that you initialized with in the first at time t, then over time you will lose points. And so typically in a real world scenario, every now and then you will have to consider new points as well. So you have to start new tracks, as this is called. So this is, sometimes this approach is called the Klt Tracker. Klt stands for Kanade, Lucas, and Tomasi. So this is Kanade and Lucas did the optical flow, and then together with Carlo Tomasi they extended that to this tracking. And the teapot that I showed in the beginning, that is an example of such a Klt tracking. And the Klt Tracker is one of the most common trackers in computer vision. Partially because it's simple and partially because it works fairly well. Because it's simple, it's also quite fast, so it's fairly easy to get this working in real time. 30 frames a second is no problem. The same approach, and I wanted to mention that, can also be used for feature point extraction. So remember in 81, Lucas and Kanade tackled the optical flow problem with that so-called structure tensor. sometimes you want to find, for a lot of computer vision applications, characteristic points. Points where you can, for example, estimate flow, estimate motion. For example, if you want to do tracking here, you have a moving camera. These points where the board ends, they may be helpful because these are points where you have some structure in different directions. This point, on the other hand, is not going to be very helpful, because if you take structure around here, you don't see much. And so the question is, how can we reliably extract points? We saw that you can use the determinant. There is a somewhat the more sophisticated approach to solve this problem that somehow goes more into detail about the eigenvalues of this matrix M. The determinant is the product of eigenvalues, and the question is often, how do you weight the different eigenvalues? The matrix M has, here we have it, 2 eigenvalues, and then the question is, how do you measure the size of the eigenvalues in order to determine whether you have sufficient structure? One approach that was proposed by Wolfgang Förstner in 1984, and a few years later by Harris and Stevens in 1988, it is now known as the Harris corner detector. Has anyone heard of that before? I see a number of people, yeah. So this is a very famous detector, Harris corner detector. The name is misleading, as you can see. It was proposed by Förstner in Germany, who is now in Bonn, who actually visited us 2-3 weeks ago. He's still active in computer vision these days. He devised this detector, he published it, but that is typical for science in many domains. You publish something and the world doesn't notice. That is very unfortunate, and so nowadays we are not only aiming to publish things, but then typically what is part of a research career is you have to market your things. You have to make sure that the right people will actually find out about your paper. And this is increasingly difficult because there's more and more people publishing more and more things. There's hundreds of conferences, there's tons of journals on image analysis. No one can read all the proceedings of all the conferences, no one can read all the journals. And so the question is, how do I make sure that people actually find my paper? Today, to some extent, this is made easier by Google. If you put your paper online and someone searches the right keywords, so you got to make sure your paper has the right keywords in it, that people can find it. And you want to make sure that your paper is online. If a paper is not online, it's very hard to actually, for anyone to actually find it. Chances are people are not going to see it. And so these are issues, and in '84 there was no internet at the time, so Förstner could not just put his paper online and make sure everyone heard about it. Some of the earlier papers also were published, and I talked to him about this. He's a bit sorry today. They were published at fairly small conferences and workshops where maybe, say, the Anglo-American community did not find out about it. Now people know about this work, but often once the machinery of citation starts going and everyone cites Harris as the inventor, then it's often too late to change things. It's very hard to stop that. You can imagine if a work like the Harris corner detector is influential, citations have a tendency of growing exponentially. And if you then come a few years later, it's like having trying to stop a wave by, saying, wait a second, this is not right. So this happens frequently. Nowadays the detector is often called Harris, but do keep in mind it was invented by Förstner in '84. The way it works is you set up the structure tensor, and you see there's one slight difference. The standard structure tensor was just summing these gradient values over the window. What we do now is we weight them with a Gaussian. And that is to say, we want to give more emphasis to the center of the image where we actually want the velocity, but we need a certain vicinity to aggregate structural information, and so we weight this vicinity with the Gaussian and say the matrix and also the vector B equivalently are weighted with the Gaussian. And that basically, the way you can get the Gaussian is quite easy. If you go back to this original energy, you can just weight the flow constraint squared with the Gaussian. And you can imagine then if I expand the square, every expression will be weighted with that Gaussian. And so the structure tensor here that we had here is also going to be weighted with the Gaussian. So x is the center point, x prime is the current point, and the Gaussian is such that the further away I go from the center, the smaller the weight. So I can do the same as with a standard structure tensor, but I put more emphasis on the center. The differences are not huge, one should say, but typically the estimates will be improved because you emphasize the center more than the surrounding area. Once you have that structure tensor, instead of just computing the determinant and checking if it's 0, you can compute the determinant plus some kappa times the trace squared. Why that is, there's a lot of heuristics in that, one should be honest. The determinant is the product of the two eigenvalues of M. The trace is the sum of the two eigenvalues of M. And by having both of these, you have, in some sense, a quantity that is a little bit more robust in practice. And then again, you take some threshold theta and you check, is that quantity C larger than theta? So it's in some sense quite reminiscent of what Lucas and Kanade did for flow estimation. If you apply this Förstner detector to an image, this is what it looks like. So you can see it nicely selects indeed a lot of points that are corners. And this is why it's often referred to as corner detector. And it is still used frequently today because it's simple to implement, because it's fast, and because it works fairly well. How many points are selected here? You see there's about, 100 points here, something like that. That depends on how you set the threshold. If you take a lower threshold, then more points are going to be labeled as discriminative. It also depends on the contrast. If you reduce the contrast in the image, I mentioned that, then all these quantities will get smaller, and as a consequence, the fewer points will be selected. So the same image the algorithm can find fewer points if you just reduce the contrast. This is a bit unfortunate. You would like something that doesn't really depend on contrast, and there's ways to kind of make this more sophisticated, but essentially this is the idea here. Now I come to the wide baseline case. So we saw with Lucas-Kanade we can do small displacement tracking. And just to remind you, this tracking that I showed here, so this approach where you select points, you assign a velocity, and then for the moved points you continue assigning the velocity. This is shown in that T example that I had here. So this is exactly this Klt tracker. You find points that are sufficiently discriminative, and you assign a motion, and then you track them over time. But what you see if you go very close on this sequence is that there tends to be a little bit of drift, because the velocity is estimated not perfectly at any given moment. And then if you continue estimating velocity at the new location, then basically you can think of an object moving and you have a little window, say in some area, but the window drifts a little bit with respect to the structure because the estimates are slightly incorrect, and so from one frame to the next you're not exactly looking at the same structure anymore. How much drift there is depends again on how challenging the sequence is, on how well your implementation works. You try to minimize the drift, but this is not trivial. It's a difficult problem. Here's the wide baseline case. This is an extreme case of wide baseline. Here we have two images of the more or less the same scene. It's not exactly the same scene, but more or less. And this is extreme case of wide baseline. And I wanted to show you this because in principle, this is part of computer vision. Someone says, hey, you can do reconstruction from two images. Here's two images, reconstruct, right? And then you have two images like this, and indeed there is information here and here, but it's very hard to find correspondences because the displacement is very large. So a point, for example, on the head of this figurine here is in that region of the image, so the displacement relative to where it was before is about half the image size. So it's a large displacement. Not all points undergo large displacements, but many do. There may be points that didn't move much, but most of the points moved a whole lot. In addition, many points don't have correspondences. For example, if you look at that poster in the left image, where is it in the right image? Nowhere. It's not there. So if I say, well, tell me the corresponding pixel in the other image, that question is not solvable. In many cases, there is no corresponding pixel. It just isn't there. Or if you take that point here, say the R of Perrier, in principle, the point is in the image, but it's occluded. It's no longer visible because of substantial rotation of the camera. The same point is actually behind some other structure. And this is very nasty, right? In optical flow, one of the key assumptions is that velocity from one point to the next is the same, so that the velocity is constant in the Lucas-Kanade. Then I mentioned the horn and shunt doesn't make that assumption, but it assumes that the velocity changes smoothly from one pixel to the next. In such cases, this is all not true at all. Here, for example, you see this mannequin is on the left of the bottle, and here it's completely on the right of the bottle. So we have actually structures passing each other, and this makes correspondence a really nasty problem. To my knowledge, there are not a lot of algorithms that can handle such extreme cases. To some extent that works. There are algorithms that can do things. For example, algorithms that can find correspondence for the Einstein images. This is by now almost solved, one could say. The reason being that the Einstein images are planar. This is a flat surface, and so we'll see later on there is a transformation that takes this planar structure to that planar structure, which is called a homography, and estimating homographies is a fairly solvable problem. And so this can be done, and also finding descriptors that actually find correspondence here is also doable. Because the structure differs from, so if I compare a certain area here to its corresponding area, the difference can be modeled fairly well with such homographies. This is not the case if you have objects that have substantial 3D information. So planar structures are nowadays fairly well studied. Non-planar structures, say the mannequin, for example, is a nasty thing to treat. It's also nasty because it's slightly specular, slightly shiny, and because it doesn't have substantial intensity variation. It's fairly constant in color, whereas the Einstein image has a lot of brightness color variations. So there's a lot of texture here, and on the mannequin you have fairly little texture. Glass bottles are really bad. I don't know, there's not a lot of algorithms that can handle glass. The reason being that what you see here, there's specularities, like there's a bluish color here, and there's certainly no bluish color on the other, because things change. Because the observed color depends on the viewpoint. What we see here is a reflection of some light in the glass, and where the reflection is on the image depends on where your camera is. So brightnesses change drastically. In addition, you have this semi-transparency, so I see green here, but to some extent I see the background coming through because it's transparent. And what background I see depends on, what's behind it from that vantage point. So that makes glass and specular, metallic, shiny objects really nasty for computer vision. Yes, this is the key problem in the wide baseline setting. Finding correspondence is very hard, next to impossible. Nevertheless, we can start with these local approaches that I just introduced, and we can check how much we can extend them to the wide baseline setting. I mentioned this issue of drift. In the small baseline case, you have drift, meaning the window where I estimate motion with respect to the real object over time in my image sequence, it drifts. It moves away because each estimate of the velocity is slightly off, and so the window is slightly off. What you can do, I didn't mention earlier, but what you can do as a remedy is you can say, well, I want to find the correspondence not just from frame t to time t+1, but I want to always link the same patch back to the first image. I had my teacup in the first image, I tracked from image 1 to image 2, from 2 to 3, and now I can say, am I still looking at the same patch? So I can try to find correspondence to image 1 as well. You can do that. This is a remedy. It allows to model larger displacements and hopefully works better. But you can imagine the key problem with this approach is the computation time will go up drastically, especially if you want a consistent matching between all images that you've seen so far. Then that scales very badly with the number of images. The good thing with the standard flow techniques and the Klt Tracker is if you keep going, it only takes 2 images at any given time, and so it's quite fast. If you now say, oh, I want to, just to make sure, check to all the previous images, you are estimating flow from time t+1 to time t, t-1, t-2, t-3. You can imagine that doesn't scale well. If you get more and more images, your algorithm will just gradually slow down. And actually, it will slow down very fast, because the number of images you have to estimate flow with grows. So while this is in principle a remedy, it's not a remedy that allows for real-time performance. And so getting fast and accurate motion fields is still an important challenge. And linking back to the first image is a strategy that is typically not done, at least not in any real-time scenarios. Once you want to extend that feature tracker that I just showed you, the Klt Tracker, if you want to extend that to the large displacement case, to the wide baseline case, there are 2 aspects that are important. First of all, when you have large displacements, the assumption that the whole window did a translation is no longer valid, right? If we go back here, if I just move the camera a little bit and the scene moves a little bit, then essentially structures do a translation. But if I do a lot of camera transformation, then the translational assumption is no longer valid. So we have to go beyond translation, for example, using that affine model, assuming that the velocity in my window is affine. This also becomes important if you enlarge your window. On a small window, translation may still be constant motion may be a valid approximation. On a larger window, the affine model gives you more flexibility. It allows some deviation from constant motion. The second issue, if you do large displacement, is that the illumination constancy is typically not fulfilled. I said in general it's not fulfilled, but in a small baseline setting, in a high frame rate setting, if I don't have a stroboscope, changing the brightness from one instance to the next, it still works. This is, by the way, you know, I think it's called stroboscopes in English. In discos they have that. It's a system that flashes at high frequency, very strong lighting. I find that interesting. It shows you that even humans assume kind of brightness constancy. And if you put a stroboscope, you have a hard time actually seeing motion, right? When people move in a stroboscope, you get a very jittered kind of effect. This is why they do it. It looks nice, but it shows you that humans, this is very frequently what we see when humans get fooled. You often see that the assumptions we make in computer vision are quite similarly done in the human brain. And so the human brain can also get fooled if you have drastic brightness changes. Not maybe the sun coming out, humans can cope with that, but if you have a stroboscope, say the extreme case of brightness changes, that fools the human visual system as well. And so brightness constancy is typically not fulfilled. If I have a large baseline case, why is it particularly bad in a large baseline case? Because typically when I have large baseline, it means that the images were not taken right one after the other. They were taking one here, and then I moved over, and then I took another image, and in that long period of time, the sun came out, the lighting changed, and things changed more drastically, and so that is particularly strong in the large displacement case. What we can do is, I mentioned that there's ways to go beyond the brightness constancy, and that is we can use what's called the normalized cross-correlation. Here's the formula. It looks a bit complicated, but it's actually very simple. What you do to estimate the cross-correlation, the normalized cross-correlation, is you take your window, W, and you take all the intensities in that window, so all these the brightnesses that you have here in the window, and you compute the average brightness, and then you subtract that average brightness. This average brightness in the first image, I call it I1 bar, is the average brightness in my window in the first image, and I2 bar is the average brightness in the second image. And what I do here is, rather than working with the intensity directly, I work with the intensity where I subtracted the mean. What do I gain by doing that? I gain invariance to additive brightness changes. Assume you take the same image and increase the brightness at every pixel by some constant gamma. Then the average will be increased by gamma as well. And if I subtract the average, that gamma disappears. So I1 minus I1 bar doesn't depend on that parameter gamma. Meaning whatever expression I compute here, because whenever I look at I1, I look at it with and subtract I1 bar, it means I'm invariant to additive brightness changes. And then in addition, you don't take the time derivative, the difference between brightnesses, but you take what you see here, the scalar product. So these are all the brightnesses at any pixel x prime and at the corresponding pixel in the second image. And then you take the scalar product of these. The way you can see that is you can, let's say you take all these brightnesses, you normalize by subtracting the mean, and then you take just one long vector of these components, and what you have here in the numerator is the scalar product of these two vectors. One brightness vector for the first image, one for the second image. We take the scalar product. If these, and then what do we have down here? We just normalize by the lengths of these vectors. So we consider all brightnesses of in the first image, in that patch in the first image, as a vector, and what we have here is the length of that vector, right? The norm squared and then the square root of it. So we divide by the length, meaning we take the unit vector. So we take all components, all the brightness values, and consider that as a vector in a high dimensional space, and then just normalize by the lengths. Why do we normalize by the lengths here? We normalize by the lengths to also get invariance to multiplicative brightness changes. Yes?
To have the length, we should add those two integrals at the bottom, right?
No, this is the, sorry, maybe I should have put two square roots here. I put both under one square root. You could have put two square roots. So we have the lengths of one vector times the lengths of the other vector here. Because up here we also have the product of the two. And so what you have, the way you can see that, is if you call these vi the vectors, then what you have here is the scalar product of v1 times v2 divided by norm v1 and norm v2. And what that is geometrically is nothing but the cosine of the angle between these two vectors. So I have one vector representing the normalized brightnesses of the first image, one vector representing the normalized brightnesses of the second image in the respective windows, and then I take the angle and the cosine of it. The idea being, if the patches correspond, that value should be large. Then the two vectors should be pointing in the same direction, and then the scalar product should be maximal. And also the angle between should be 0, meaning the cosine should be 1. So this expression is clearly between -1 and 1. And in practice, if the two vectors are identical, if the patches are the same, I get a 1. And if they're very different, it goes smaller. And so the normalized cross-correlation for a good match should be maximized. This is called, this in the top is called the cross-correlation, and with the normalization it's called the normalized cross-correlation. The cross-correlation is invariant to additive changes because we subtract the brightness average here in both cases. The normalized cross-correlation due to this normalization is in addition invariant to multiplicative changes. So if I scale the image by some constant, so each color is scaled, each brightness in the image is scaled by some constant gamma. If I do that, I have gamma up here, I have gamma up here, and I have gamma down here, so the gammas disappear. They just get normalized out. And so this is how you can easily verify that this expression is invariant to additive brightness changes and multiplicative brightness change. Meaning you're in a good condition to work with brightness changes. Meaning if your brightness changes because every pixel has an increased brightness due to the sun coming out, etc., your cross-correlation is not affected. It doesn't change. And so whether two patches match does not depend on the constant offset. That is in principle a good thing, because it means we can work with substantial brightness changes. Even very extreme cases of lighting changes, as long as they're additive or multiplicative, have no effect on our comparison, on our measure of correspondence. One should be careful though, so this is not the solution to every problem in the world. As you can imagine, you know, once we have a problem, we can try to do better, and we will do better in some setting, but what we often find in science is we do better in some scenario, but then in turn we do worse in another scenario. The cross-correlation is, and the normalized cross-correlation is terrible if you want to compare a white patch and a black patch, for example. What happens if I have a patch that is constant in color? One is white, one is black. The cross-correlation, the normalized cross-correlation value is going to be 1. Why is that? If I subtract, actually it's not even defined in some sense. If I have a constant brightness patch, I subtract the mean, then this expression is 0, and so is this, so I have 0 divided by 0. It's completely uninformative. As soon as you have a constant brightness patch, the whole thing doesn't even work. And so these approaches are likely to tell you if you have a white and a black patch that they're the same. And now clearly you would say a white patch is not the same as a black patch, and an algorithm that cannot separate white and black is pretty stupid. But remember, if you want invariance to brightness changes, well, these two patches only differ by a constant brightness. Either you want that invariance or you don't. So the question really comes down to what kind of invariance you want. And often we find in this scenario, we don't actually want complete invariance. We want a certain robustness, in the sense that if I have a little bit of a brightness change, then the measure should not be affected too much. But we don't want it to be completely invariant. We don't necessarily want an algorithm to tell us a white and a black patch are the same. And so as a consequence, these normalized cross-correlations sometimes work better, but not always. It really depends on the data that you're looking at. And at that point, optical flow estimation becomes a super sophisticated problem. Not sophisticated, but a problem that invites hundreds and thousands of researchers to publish papers, because you'll always find a scenario where that assumption is not valid, but some other assumption works better, and then you get an algorithm that for this problem works well, but for others doesn't. To have one algorithm that works for everything is, of course, what everyone would like to have. In practice, we don't typically have that. The way nowadays we go about it in order to get algorithms that work reliably on typical images is that we set up so-called benchmarks. So a benchmark typically consists in optical flow. There's about 5, 6, 7 benchmarks today, and they were started even in the 90s, I think, some of the first benchmarks, and then now we have tons of benchmarks these days. They typically consist of pairs of images, always 2 images where you're supposed to estimate the flow. And in addition, there is a so-called ground truth, that is what was the real flow field. This is a challenge. The challenge with benchmarks is typically either the data set is not realistic or you don't have a ground truth. Having a data set with a ground truth and very realistic images is difficult. Because the problem is, if you have 2 images that you take from a real camera, you don't know for every pixel where it really goes. You don't have the ground truth, you just have the images, so you would need an algorithm to compute it, but you don't have the perfect algorithm. So if you take real-world images, typically it's very hard to get ground truth. Nowadays, nevertheless, we have benchmarks that are both quite realistic and that have a ground truth. And there's 2 ways to get at it. One way is that was done in the so-called Middlebury optical flow benchmark, is they superimposed an infrared pattern on the scene, a very high frequency detailed pattern which allowed them to find accurate correspondence when they took infrared images of the scene, and then they took regular images for the competition and additionally infrared images to get the true correspondence. And that way you have real-world data with an accurate ground truth, or fairly accurate ground truth. And the other way is to revert to your colleagues in computer graphics and see if they cannot simulate a realistically looking scene. And nowadays graphics is on a level where, as you know from Hollywood movies, simulated videos can often hardly be distinguished from real videos. And if you're in that regime, once you simulate the video, then you know the correspondence, because you have the 3D model, and so you know where structures went, and that way you get a ground truth. And this is a recent benchmark that appeared last year, the so-called Syntel Benchmark. And that allows you, that is simulated images, sequences. They have, realistic motion, sophisticated large motions, substantial motion. They also have, fog and atmospheric changes, things, a lot of the motion blur, whatever you get in real world videos. And still you have a ground truth, so people can devise algorithms and say, do they actually get accurate motion on real scenes? Here, to come back to the cross-correlation, the way you could solve that in this setting is you could say, I want to maximize my cross-correlation. Remember, it should be maximal for a good match of the 2 patches. And then I can say I want an affine transformation, and so the overall cost function would be like that. It looks very large, but it's actually the same cross-correlation, and it's parameterized in these parameters A and D, A being a 2x2 matrix, D being a translational offset. So these are my 6 parameters to estimate. And now I can say find 6 parameters A and D such that the cross correlation is maximized. Find the rotation and translation that maximizes this error measure, or minimizes the error, maximizes this consistency measure. This would be a way to do large or wide baseline. There are other approaches to do wide baseline, but this is an approach which basically starts from the Lucas-Kanade idea and generalizes it using the cross-correlation. I'm not saying that this is actually going to work well in practice. This is very challenging, because how do you minimize such a cost function as a function of 6 parameters? It's not a convex cost function. It's very hard to do optimization in 6 degrees of freedom if you don't have any additional assumptions. The large baseline, wide baseline matching nowadays is solved either by going to more sophisticated optical flow algorithms that build up on this horn and shunt approach and estimate smooth or piecewise smooth flow fields, or in an extreme case of wide baseline, they go to descriptors and they start by associating each pixel in an image with a very lengthy, say, 100 component vector that encodes the structure there, and that to some extent uniquely characterizes it. And then you just search in the other image for a point that has a similar structure. So it's a little bit like doing cross-correlation, except that you have a very long feature vector. And sometimes that works, in some cases it doesn't, so this is still an open challenge. Thank you.